Hello everyone, it's Mr. Spinelli. Today we're going to talk about taking derivatives using differentials. Now this is commonly not taught in classes, but I think it's just an important topic to see, and it's just a fun way to consider solving problems. Um, so what do I mean by differentials? Well, we're all used to seeing that dy dx is another way of denoting the derivative of some function f of x, where we say that y is equal to that function f of x. Um, so alternatively, dy and dx on their own are so-called differentials, and they're infinitesimally small units of height and width, respectively. So let's take a look at how we apply them. So if I've got some function, we're going to start very easy with one we know you know how to take the derivative of. That's x squared. Okay, so this is the same thing as saying y equals x squared. So what I'm going to do is I'm going to perturb or very slightly adjust these functions by adding a differential dy and dx to both the y and x respectively. So instead of y equals x squared, I'm going to add dy, because once I change the x by some small quantity dx, the y is going to change. And when I adjust the x, I have to make sure I do it in parentheses because x is being squared. I get this. So now what I want to do is I want to expand the right side. So if I expand the right side, I get x squared plus 2x times the differential dx plus dx, which is a differential, squared. So I get this. Now what you'll notice is I've got a y and x squared on both sides. Well, before I said that y equals x squared. So what I'm able to do is remove that from both sides. So I get dy equals 2x dx plus dx squared, because that is some quantity. It's an infinitesimally small width. And now what I'm going to do is divide dx on both sides. So then I get dy dx equals 2x plus dx. Well, dy dx is my derivative, and we all know that the derivative of x squared is 2x. So what about this plus dx? Well, because dx, the quantity, the infinitesimally small width in the x direction, is so small, I'm able to just ignore it because it's a negligible contribution to the derivative of x squared, which is 2x. So another way you can do that is anytime you see this dx being squared, you can eliminate it from your problem. So let's take a look at another example, because really this is just fun arithmetic, and it's really not practical when you get to some more challenging problems. So let's take a look at y equals x cubed plus 3x squared minus 5. Okay, we know what's going to happen with this, but let's go ahead and find out. We should get 3x squared plus 6x. So what I'm going to do is I'm going to perturb the x, which results in a perturbation of the y. Again, I'm just applying these infinitesimal changes to x. I get plus 3x plus dx, the quantity squared, minus 5. Now I've got to expand the right side, and ultimately I should find x cubed plus 3x squared minus 5 in that result. So I get x cubed plus 3x squared dx plus 3x dx squared plus dx cubed. So you notice these dx squareds and dx cubes are quite small, because when you square an infinitesimally small unit, it gets even smaller. And when you cube it, wow, it's tiny. So then I've got plus 3 times the quantity, x squared plus 2x dx plus dx squared and then finally minus 5. So when I distribute the 3 in, I'm going to have a 3x squared, and then I've got this x cubed and the minus 5, so I'm going to get rid of those, and then on the left, all I've got is dy, right? Because I'm going to get rid of the y. So then I've ultimately got dy equals, now I'm going to group things. I've got 3x squared plus 6x, and that is everything that has a dx with it. And then I've got 3x plus 3. That's everything that's got a dx squared. And then I've just got one lonely dx cubed. So all of these are what some people will call higher order terms. What I like to call hot higher order terms. Their contribution to this differential is so negligible that we are able to neglect them. So I ultimately end up dividing by dx, and I get 3x squared plus 6x plus the higher order terms that I don't care about. Okay? And as we said before, we knew this is what we would get for our derivative. Kind of fun, right? Let's take a look at another one. See how practical or impractical this is. Let's do a basic one. Cosine of x. Okay, we know the derivative is negative sine of x, but let's see if we can perturb it and find out. So y plus dy equals cosine of x plus dx. Oh, back to the trig rules. How on earth do I do that? Well, cosine of a plus cosine of b is cosine x cosine dx minus sine x sine dx. Huh. What does this mean? Well, let's see what we can come up with. Well, what is dx? It's some infinitesimally small unit. So we can kind of think of it as 0. Well, what's cosine of 0? It's 1. So I get cosine x. And then sine of 0, that's 0. So now I've run into a problem. Well, what you may or may not learn is that sine of x for very, very small x values can be approximated as x. So sine of dx can be approximated as simply dx for infinitesimally small values. So I have minus sine of x times dx, and then I've still got the y plus dy on the left. I notice that I've got y and cosine of x on both sides. Those are the same, so I end up with dy equals negative sine of x times dx. Divide by the dx. I get dy over dx equals negative sine of x, which is what I expected. Now, I kind of did some hand waving with this. Now, there's numerous textbooks and websites you can go to read about this. But this is just one example of why differentials, in order to compute derivatives, aren't always the most practical. So um, I just wanted to give you a little peek. And this gets even uglier, and I won't finish this entire problem. But if you've got y equals, well, let's go ahead and finish this one. Y equals 1 over x. This is very basic. So you know that y prime, or dy dx, you know it's going to be equal to negative 1 over x squared. But let's see why this method of differentials becomes even more impractical for this particular problem. So I've got y plus dy equals 1 over x plus dx. I'm going to do something a little odd here. I'm going to rewrite this right side as 1 over x plus a. And I don't know what a is. Why on earth am I doing this? Because I want to ultimately eliminate y from both sides. All right, that's my goal. So then what is this a? Well, let's switch colors to figure out what this a is. So a is going to be equal to 1 over x plus dx minus 1 over x. So I'm kind of just focusing on this part of the equation right here. So I've subtracted the 1 over x to the other side. Now I've got to get common denominators, which means I'm going to have x minus x plus dx all over x times x plus dx. Okay, so that's what a is, which if I simplify it, it's simply negative dx over x times x plus dx. All right, so back to this. Let's go back to blue. So I've got y plus dy is equal to 1 over x plus a, and I just found what a is. A is negative dx over x times x plus dx. So what do I notice? I can get rid of my y and 1 over x. So I've got dy equals negative dx over x times x plus dx. Divide both sides by dx, and I get dy over dx equals negative 1 over x times x plus dx. So now in this context, I have to realize that dx is infinitesimally small and essentially just make it go to 0. So I get negative 1 over x times x, which is negative 1 over x squared. So there's kind of some hand waving, and you got to stop and think about what's going on. And you have to know when the right and wrong time is to say dx is approximately 0. So it's very difficult to solve problems like this. And just imagine if I made 1 over x squared plus 3x. Your idea of solving for this so-called a that I did in pink gets very, very cumbersome with algebra. But I hope you enjoyed this idea. I would invite you to look at beautiful graphs that people have made where they show some function, and that function can be any random thing. And what you want to do is take a look at some point x and consider what happens when you move really small over to the right, x plus dx. And if you find the slope between those two lines, you know that it's x plus dx minus x all over, well, you went from y to y plus dy. So this portion right here is your change in x, which is just dx, and your change in y is y plus dy minus y. So ultimately you have a change in y over change in x, dy dx, which is why the method of differentials works. So I invite you to explore this online for your own being and enjoy your day.